Hello, sir, and my fellow batchmates. My name is Adrish Aditya. I am 5th sem ECE student from Cooch Government Engineering College, and my presentation topic is pulse code modulation. So, what is pulse code modulation? Pulse code modulation is a modulation technique where an analog signal is converted into a digital signal by simply following three main steps. First is sampling, second is quantizing, and third is encoding. And encoding is done in the form of binary numbers, and it enables a reliable storage, and the transmission of signals is done by making it less prone to the noise and more compatible with digital communication systems. So at first we needed a PCM generator, which helps to create a digital pulse code modulated signal or a PCM signal. So at first we will discuss about the block diagram. So that block diagram shows that the analog message signal is passed to three sections. First is the transmitter section, then is the channel and repeater section, and third is the receiver section. So we will discuss about the transmitter section. So the here the analog message signal is first flows through the LPF or the low pass filter to remove high frequency noise. Then the sampler takes the discrete samples of the signal. So sampler is done to discrete the continuous signal. That is converting the continuous time signal to discrete time signal. Then the signal is passed to the quantizer. To the quantizer, we use the quantizer to approximate the signals, approximate the digital signals. Then it passed to the encoder, and encoder changes this quantized value to a binary code, which becomes the PCM output into a channel. That is a PCM output into a channel. Then during the transmission, we use the regenerative repeaters. Regenerative repeaters are used to restore the signal quality and reduce the noise effects. Then it flows to the channel, and then we again use the regenerative repeater for the same purposes. Then we get a channel output signal. Then at the receiving end, the signal goes to the regeneration circuit or regenerative circuit to improve its strength. Then it goes to a decoder to convert the binary PCM value that we get as the PCM output into the quantized values. Then we use a reconstruction filter. We use a reconstruction filter that smooths the signal to get back to the original analog waveform, which is finally delivered to the destination. So we can say in short that the PCM converts an analog signal into a digital form for transmission, then back to the analog at the receiver, ensuring high quality and noise resistance. Then we will discuss about the steps in PCM. We say that there are three main primary steps in PCM. That is the first is sampling. That is taking the discrete samples of the continuous time signal. So at first we know that we have to know that what are the three types of sampling. Sampling can be of three types actually. The ideal sampling, that is instantaneous and the perfect pulses. Second is the natural sampling, which follows the signal's natural shape. Uh, the flat top signal, that is a constant level during each sample. We said in the natural sampling that the signals follows the natural shape. That means it follows the direction of the continuous signal. We can see here that it generally follows the natural signal, and then it discretizes the signal. And in the flat top signal, that the top of the signal becomes flat, as a result of which we can actually lose the informations of many signals. So you can say that the natural sampling contains actually more information than the flat top signal. Then we have quantization process. What is done in the quantization process? That is the approximating sample values to fixed values, and the quantization is done by quantizer. So there are two types of quantizer. First is a uniform quantizer. Second is a non-uniform quantizer. Uniform quantizer are generally of two types. That is mid-rise quantizer, mid-rise uniform quantizer, and mid-rate uniform quantizer. And the third process is the encoding process. And here, what is done? That is the quantized values is converted into binary values or the binary form or the binary digits. Now we'll discuss about the PCM encoding process. Here what is done? Here analog signal is passes to the PCM encoder where three main processes performed, that is the sampling, and after sampling we get a PM signal, that is a pulse amplitude modulated signal. Then it goes to the quantizer or and the quantizing is done. Then you get a quantized signal, and at the end we goes to the encoding process, and as a result of this quantized signal is converted into a digital data or in a binary format data. Now the graphical representation of PCM. Here, at first we get a continuous time signal, that is the analog signal, and then the signal is sampled. Signal is sampled by taking a discrete values. Then we done the process quantization. We actually take values which close to the integers. That means if there is something like value like 1.7, the closed integer number is 2. So the value is taken as 2. So in this process, uh, this quantization is done. That shows that's the graphical representation of the quantization process. Now we'll talk about the quantization noise. Actually, due to the approximation, we actually get the signal which is not like that the original signal. So actually, when we quantize an original signal, we generate an error. That is the quantization noise. That error is the quantization noise. This error is nothing but error is E, which is described in terms of volt, is equals to the xq of NTS and minus xn of NTS, x of NTS, while xq of NTS is the quantized sample and x of NTS is the original sample. So here is the graphical representation of that the quantization process, and as a result of which we get a noise. So we will discuss about the step size. This step size is the a max minus a min by number of quantization level. A max means the maximum amplitude signal. That is the maximum amplitude of a message signal, and a min is the minimum amplitude of a message signal. So that is the maximum amplitude is what, x of m, and minimum is minus x of m, and divide by q. তাহলে x of m minus of x of m, that is 2x of m, minus divide by q, that is the step size, which we represented using delta. Then we get the what we get the maximum error. Maximum error we get as the delta by 2. Okay, so we get that after we half into 2xm by q, we get that the maximum error formula is xm by q or the delta by 2. And here the quantization noise is uniformly distributed. Here the quantization noise is uniformly distributed. So we uniformly distributed this noise, and we get the values of f of error equals to 1 by delta when the error is between minus delta by 2 and plus delta by 2, and otherwise it is actually 0. And here actually the mean is 0. Here the mean is 0. So we actually calculate the variance of noise, and with variance of we know that the variance of noise means the expectation of e square, that is error square, and then we write the formulas, and then we limit the integration, that is from minus delta by 2 to plus delta by 2, and then we completed the integration process, and actually we get that the variance of noise is the lambda square by 2, and from that we get the normalized noise power, that is p of noise, that is lambda square by 2 when the value of resistance is actually 1 ohm. Then we'll discuss about the SQNR, which is very important, and SQNR is nothing but the ratio of signal power to quantization noise power, that is the p and the p noise, and we get the p that is the signal power, and lambda square by delta square by 12 is actually the normalized noise power which we get previously, and we then solve, and we get that 3pq square by x is x of m square, and we get that the SQNR formula is 3pq square by x of n square. Then we can modify the formula, like we can put that q equals to 2 to the power v, that is quantization level in equals to 2 to the power number of bits. Then we get squaring this 2 to the power v, we get 2 to the power 2v, and we get SQNR equals to 3p into 2 to the power 2v by x of n square. And then we can again modify the formula by putting the normalized input voltage, that is plus minus 1 volt, that is we taking xm equals to 1 volt, and as a result of this we get the formula 3p into 2 to the power 2v. Then we can assume that the signal power that is less than equals to 1, so that we can again get that SQNR is less than equals to 3 into 3 to the power 3 into 2 to the power 2v. And actually this is a mistake here made. So if we cut this, and we get that the SQNR less than equals to 3 into 2 to the power 2v, and SQNR in the decibel is less than equals to, we take a 10 log 10, in case of power we take 10 log 10 into 3 to the 3 into 2 to the power 2v, and as a result of this we get that is that SQNR in decibel is less than equals to 4.8 plus 6v. That is the number of beats. So, what is the transmission bandwidth in PCM? Transmission bandwidth, we get at first we have to know that we that is Q equals to 2 to the power V, while Q equals to that we already discussed that total number of digital levels, and V equals to number of bits per sample. And what is number of bits per sample? That is the signaling rate. That is R equals to V into F of S. That is number of bits per sample into F of S. F of S is the number of samples per second. And most important is the bandwidth. Bandwidth is equals to the half of the signaling rate. That is the half of R. That is R, we get that V into F of S. So half into V of Fs. So bandwidth we get a less than equals to half into V into 2 of Fm. That we get that Fs less than equals to 2 of Fm, which we get from the sampling theorem. So bandwidth is less than equals to V into Fm, where Fm is the maximum message frequency. And PCM of speech signals. The significant spectral range of speech signals is 300 to 3400 hertz or 3.4 kilohertz. And we know that Nyquist rate is Fs equals to 2 into Fm. So we take the maximum speech frequency, that is 2 into 3400 equals to 6800 hertz or 6.8 kilohertz. And practical sampling rate is actually 8 kilohertz, which is chosen for design margin and for easy system implementation. So we take 8 kilohertz. And quantization level, if there is a quantization level of 256, so we get number of bits is 8 bits per sample by putting that log to Q formula or log to L formula. And there is data rate, that is R equals to V into F of S. So we get 8 into 8000, that is 64 kbps. So now the bandwidth requirement for PCM signal is, from communication theory we get that the maximum 2 information bits per second per hertz of bandwidth can be flow to flow at less prone to noise situation. So we get that the minimum bandwidth is data rate by 2, that is the 64 by 2 equals to 32 kilohertz. That is the bandwidth for the PCM speech. So now we'll discuss about the PCM advantages and disadvantages. So we first say that the PCM is very less prone to noise. There is a high noise immunity, less error detection and correction. Error can be easily detected and can be corrected, and it is very much suitable for digital storage and transmission. And there is disadvantages, that is which requires a very high bandwidth, and it is actually more complex than the analog communication system. We can tell about the applications of the PCM, that is in our electronics and telecommunication field. It's highly used. It is used for audio recording, and it's used for digital radio, TV, and radio transmission. So in the conclusion, we actually get that the PCM is the backbone of the modern digital communication due to its reliability, accuracy, and compatibility with digital systems. And to complete this presentation, I took help from the classroom notes, which were discussed in the class, and the electronics notes from the PCM basics. We get that from a web link, and Gigs for Gigs web link, that is a PCM in digital communication. I also took help from these two web links and the classroom notes. With this, I want to end my presentation. Thanks to everyone.